let's start again. Good, okay. So first of all, thank you so much for opportunity to be here. It's amazing to be in Rio and be able to listen to many good talks. So I really appreciate that. And today I will hopefully contribute a little bit to this poll of talks. We'll see. Okay, so what I'm going to present is a joint work with Matthew Buckland, Brett Kolesnik, and Rivka Mitchell. Rivka is one of the participants, but she didn't sleep much this night, so not sure if she will show up. Okay, and the whole talk is about some generalization of tournaments. Okay, so for the outline, first I will bring up some classical results about tournaments. They might not be well known, but they are sort of maybe not too hard to prove. But surely, I mean, I find them nice. So I hope you'll find them nice as well. Then I will introduce some kind of generalization that we considered with co-authors. And then I will show you some generalizations of the results for the standard stuff that hold for our model. Okay, and then hopefully I'll have some time to show you some sketches of the proofs. That's the idea. And before starting, most of the talk will be very combinatorial. The holy grail for us will be to, at the very end, prove some mixing results for some random walks. But in order to do that, we need to prove many combinatorial propositions about the model. So the whole body will be very combinatorial. Okay, so the base for us will be classical tournaments. Okay, and what is a tournament? Basically, the idea is that we have n players, and every pair of them plays a game. And in every game, there is one winner and one loser. Okay, and the way they're probably usually drawn is that, okay, we have dots for players, we have oriented edges for the games, and every game has an arrow pointing out from the winner. Okay, so yeah, loser always gets the tip of the arrow. Okay, so that's the model. Important thing is that, okay, every two players play a game together. Okay, and one natural statistic to consider when thinking about tournaments is, okay, how many wins are there? How many games has a player won? Okay, so with every tournament, we'll associate a win sequence. Okay, and we label our tournaments. Okay, so every player has a label, 1, 2, 3, blah, 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 n. Okay, and the win sequence will be just the out degree sequence of the graph. Okay, so we can see player 1 won 2 games with player 2 and 3. So he got a 2 on the first position. Player 2 won 1 game with player 4. Okay, so this is 1 point here, and etc. Okay. Okay, so every tournament has a win sequence. And therefore, maybe natural question is to, okay, so what is the family of all possible win sequences? And this is a natural question. It was studied last century. Okay, and yeah, so let's think a little bit about this question. Okay, so what are the okay, suppose I have a win sequence. What can I tell about it? Okay, so first thing is, okay, I have entries to games. Yeah, so sum of all wins is entries 2. Okay, this is some easy abstraction. Okay, but there is a little bit maybe more subtle. Okay, so suppose I take some k players. Okay, then all the games between them are caged between them. Okay, so all the wins between them are also dispersed between them. Okay, and there are k choose 2 games between the k players. So for every k, sum of any number of wins of k players must be at least k choose 2. Okay, and it turns out that this is already enough. Okay, so if I have a win sequence, if I have a sequence which satisfies these 2 conditions, then it turns out that I can build a tournament having this win sequence. Okay, and this is a theorem attributed to Landau, which can be restated in a majorization condition. Okay, so these two conditions, they can be rewritten as some form of majorization by sequence 0, 1, 2, 3, up to n minus 1. Okay. There are multiple proofs, some cute, some algorithmic, but we'll not talk about them now. Okay, but maybe about like some small comments about the theorem itself. So this sequence 0, 1, blah, 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 n minus 1, this is also a win sequence. Okay, it's a win sequence of a transitive tournament. Okay, and what is a transitive tournament? It's a tournament where like the outcome of the game is decided by the index. Okay, so if I have a low index, then I lose with players of higher index. Okay, so player 1 loses all the games, so he gets score 0. Player 2 will win 1 game with player 1, so they will get score 1. Okay, and the strongest player will win all the games, which are n minus 1. Okay? And the second comment, like more about this majorization condition, is this majorization, it can be interpreted in a geometric way. So to be majorized, okay, if you consider all the permutations of if you don't care about the order of the order statistics of the win sequence, then to satisfy the majorization condition is to be inside or on the boundary of what is called permutahedron. Okay? Permutahedron is a convex hull of all permutations of this sequence. Okay, so there is some nice geometric interpretation of the win sequence. These are all integer points within the permutahedron. Okay, yeah. Okay, and now, okay, we quite well know we quite well understand the set of all possible win sequences. So maybe we can ask more refined questions. So, okay, so now suppose maybe it's a little bit perpendicular question. Like, let's fix some win sequence. Okay, then, and usually there will be many tournaments which yields this win sequence, right? Okay, can we say something about that? So that's a good question to ask. Okay, so maybe a useful thing to consider is our cyclic triangles, which are very simple, but okay, why not? Okay, so if you have a cyclic triangle, which is, for example, like here, then if you reverse all the arrows, if you switch it, then it doesn't change win sequence. Because, yeah, at every vertex I have 1 win, 1 lose. I reverse it, I have 1 lose, 1 win. Okay, so the win sequence stays the same. Okay, so now the idea is that, okay, let's fix some win sequence, consider all the tournaments that have this win sequence, and now we can construct some kind of meta graph. Okay, we connect to tournaments whenever I can flip one cyclic triangle to get the other. Okay, and this this meta graph, we'll call them like interchange graphs. Okay. So the first slide is an example of such a thing. Okay, and it's for the wing sequence that is up there. Okay, and we start from the lower down corner, and if you see, the red edges will be comparison of the lower down corner tournament. Okay, so here you make one step, and this is reversal of this triangle. Okay, if you make step here, this is reversal of the left lower triangle, and etc. Okay, and you draw all these edges, and you get some big, nice, symmetric metagraph. Okay, and usually, like this metagraph, it will have exponential size in n. Yeah, I have some polynomial number of triangles that I can switch. This will, like the whole space will get crazy. So it's going to get exponential. Okay, so what can we say about these interchange graphs? Okay, so it turns out that for any win sequence, every interchange graph is connected. Okay? This means that if you take any two tournaments of the same win sequence, then you can switch single cyclic triangles to get from one to the other. Okay? So you can perform these local steps to get anywhere of the same win sequence, which is nice. It's some combinatorial inductive proof. Okay, the second thing, it's bipartite. Like at every step, I swap odd many edges, so you can anchor some graph and then yeah, distinguish two classes of tournaments based on the parity of number of edges that differ. Okay, so it's bipartite. And it turns out that, okay, for every win sequence, you can also prove it's regular. Okay, what does it mean? It means that if I have two tournaments of the same win sequence, then they necessarily have the same number of cyclic triangles. Okay, and these graphs were maybe first formally studied apparently by Buraldi and Lee, and they proved some bounds on the diameter of these interchange graphs. Okay, and the proof of regularity of this graph is actually not hard. It's a one-liner. It's a cute one-liner, so I'll show you. Okay, so in the square brackets, I will denote, okay, I fix some tournament, and I'm counting number of cyclic triangles in this tournament. Okay, so I have some tournament. I count them, okay? So one way to express the number of the cyclic triangles is actually to count non-cyclic triangles. Okay, so in total, there are n choose 3 triangles, and I can just subtract these which are non-cyclic. Okay. Okay, but the non-cyclic triangles, actually there is just one kind of them. Okay, if you have 3 vertices and the orient edges, yeah, either it's cyclic or it looks like that, it turns out. Okay. Yeah, it looks like that. And the interesting thing about this graph is that, okay, it has exactly one winner, like double winner. Okay, so in this graph on 3 vertices, there is one vertex which have 2 arrows which are winning, and exactly one vertex. Okay, so a different way to count these triangles is to just like iterate over all vertices and count all the pairs of edges which are outpointing. Okay, and this will give you the same thing. Okay, but we just phrase the number of cyclic triangles as some function of the values of win sequence, yeah? So it doesn't matter what was the tournament that we started with. Okay, so it's regular for any W. Okay, any questions? Okay, And it turns out there's a bit nicer way to phrase this formula. Okay, as simple as it is, we can phrase it a little bit better. So if instead you will consider something what we call score sequences, okay? And now by score, I mean winner will get plus half point and loser will get minus half point. Okay, so the score sequence is just shift of the win sequence. Okay, then the score sequence of the transitive tournament will look like that. You know, it's again shifted. This 0, 1, 2, blah, 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 and 2 minus 1 is shifted. And this formula can be phrased in like some distance-like form. Okay, so maybe expressing the number of cyclic triangles, we will just deduct the square length of the score sequence from the square length of the transitive tournament score sequence. Okay, and divide by 2. Okay, and this has some connection to this permutahedron. So if you shift this permutahedron to the center of origin, then the radius will be just the first, the radius squared of the permutahedron will be the first term. And our score sequence will be, our S will be some point sitting in this permutahedron. So the closer you get to the boundary, the less cyclic triangles you have. Okay? If you get to the vertex of this permutahedron, then you're a transitive tournament, and transitive tournaments don't have cyclic triangles. But you get 0, so everything is fine. Yeah? So there is some geometric interpretation of this simple formula. Okay. And now it becomes a more refined question. Okay, so fix some win sequence, look at all tournaments which realize this win sequence. Okay, can we sample these tournaments uniformly? And okay, because these families of exponential size and it gets a bit crowded. There are some, these cyclic triangles, they overlap, so it doesn't have any nice, completely product-like structure. We expect the exact count to be hard complexity problem. Okay, so it's unlikely that we'll be able to sample quickly, precisely from uniform distribution. Okay, but again, if not exactly, then maybe you can perform some approximate sampling. And for approximate sampling, we can just consider Monte Carlo Markov chain on the interchange graph. Okay, so what I will do, I will start at one vertex, then perform lazy, simple random walk. And after some time, I will hopefully converge to a distribution which is close to stationary. Okay, and lazy, because the graph is bipartite. Yeah, so I want to be lazy because, yeah, and simple, the graph is regular. So since the graph is regular, then the stationary distribution will be uniform. Okay, and okay, to prove, okay, all we need to know now that it's a reasonable algorithm, say, so that it converges in a quick time to the stationary distribution. So in order to do that, we will need to prove that this chain rapidly mixes. Okay, so by rapid mixing, okay, what I will go for, maybe to remind those not that familiar with rapid mixing, I will just try to prove that there is some time which is polynomial in the number of players, so that the distribution after t steps is at most constant far from the small constant from the stationary distribution. And the thing is that it's not, again, not super hard fact that one can get any epsilon instead of 1/4 by increasing the time by log over 1 over epsilon. Okay, so we are just aiming for the constant. Okay, and this problem was studied in 1990s, and the first one to consider this lazy simple random walk on interchange graphs were Cannon, Tetali, and Vempala. And they managed to prove this rapid mixing for win sequences for tournaments which are sort of balanced. Okay, so by sort of balanced, I mean that every vertex has won more or less the same number of games as they lost. Okay, so if I restrict my attention to this sort of regular win sequences, then they manage to prove the rapid mixing. Okay, but not much later, the Lisa McShine proved like just killed the problem in some sense, because she proved rapid mixing irrespectively of the what win sequence I have. Okay, and the proof uses path coupling method, which I will talk briefly about. It's a very cute application of the method, and I find it nice. Hopefully you'll find it nice as well. And the proof was much shorter than the weaker result of the previous authors. Okay, so this is the story of classical tournaments. And now I would like to tell you more about the generalization. Okay, so any questions until? Good. Okay, so now how do I generalize the tournaments? So again, I will consider n labeled players, and every two play a competitive game. Okay, but now in addition, every two will play a collaborative game. Okay, so there are many edges, but the idea is that every two play a competitive game, and in addition they play this collaborative game, and the collaborative game can be either won or lost by both players, this collaboration. Okay, so this is kind of tournaments that I will study. And now I'll forget about the win sequences. I'll just care about score sequences. It turns out, okay, maybe this shifted version is a better statistic to care about. And now every win will give you plus half point. Every loss will give you minus half. Okay, so yeah, so maybe let's study one score in our graph. Okay, pointer died, but it's fine. Player number 1, lower up corner. If we care about the competitive edges, then they won 2 games and lost 1, so it's plus half. And it's the same about they won 2 collaborative games, the red edges, and lost 1 collaborative game. Okay, so they get 1 point in total. Okay, and I get some score sequence. Yep.
So is capital D equal to 2 here, or does D have a different meaning for this terminology? Say D type.
It will be clear in a moment. This is a D root system concatenation, so there is no number here. Okay, and now I would like to also introduce 2 more models. Okay, and now it looks a little bit arbitrary, which I'm sorry about, but it will be a bit clearer in a second. Okay, so there are 2 more models, B and C. So I consider competitive and collaborative edges in both of them. And in addition, every player will play a single solitaire game. And in type B, the solitary game can be either won or lost. And in B, I get plus half point or minus half for winning, losing. And in the C type, I will get double. Okay, so I will get full 1 point for winning or losing. Solitary game. Yeah, so these 2, they differ by just this weight on the solitary game. Okay, and for a bit of terminology, like on the right-hand side, we'll call them loops. On the left side, we'll call them half edges. Okay, and this might look very arbitrary now. So let me maybe argue why it's not that arbitrary. And the motivation comes from algebra. And if we come back to this consideration of permutahedron, then it can be interpreted as a sum, as a Minkowski sum of vectors. Okay, so what do we do? EI will consider the basis vectors of Rn. Okay, so EI has 1 on the ith coordinate. And I can represent the permutahedron as a Minkowski sum of intervals, okay, which are somewhere in space. Actually, this is why the permutahedron is probably defined, and only then Rado showed that it can be present as a convex hull. But okay, this is the details. Okay, so this permutahedron can be represented in this way. And this polytope, okay, we know that okay, integer points correspond to Wien sequences. But more than that, there are some nice combinatorial aspects that can be proved about it. Yeah, so the volume is actually just the number of spanning trees of a clique. And also the number of these Wien sequences, they correspond to, like this is the just number of spanning forests of Kn. Okay, so there's some nice combinatorics going on behind this permutahedron. Okay, and now when you look at this permutahedron, then it's driven by these differences of basis vectors. Okay, and actually, this set of basis vectors is one of examples of what is called root system in algebra. Okay, we are probability people, we are combinatorics people. Like the first time I saw root system was also when coming across here. And it turns out it's a very well-known studied object in algebra, which underpins like many objects that appear in algebra. Like for example, it's crucial for classification of simple Lie groups, yeah, and other stuff. Okay. Okay, and the thing is that for our purposes, we can think about root systems as just very symmetric sets of vectors. Okay, so this set of vectors, if you draw it in space, then it will turn out that it's closed on many symmetries. So it has not very nice geometry. Okay, so there is some connection between, okay, from tournaments to permutahedron, from permutahedron to root systems. But there are more root systems. And there is okay, like root systems are well-defined objects, and there is a full classification of them. And it turns out that there are just 4 infinite families of them, A, B, C, and D, indexed by n, and some exceptional types. And one of these exceptional types corresponds to Leech lattice, which might be more known object, which appears also in many places. Okay, so the idea is that okay, classical tournaments correspond to A. I have types B, C, and D. Can I find some combinatorial objects corresponding to B, C, and D? Okay. And A, D, B, C, again, they are families of vectors. I recall EI, these are basis vectors in Rn. Okay, and one of possible representations of these root systems are like that. Okay, these are some families of vectors in Rn. Okay, so classical tournaments correspond to A. And maybe a bit better picture, like how they correspond to AN, is that for every vector that is in root system A, okay, they are paired. Okay, there are like sort of for every vector you have for every vector V there is minus V in the family. Okay, so when you build a tournament corresponding to some orientation of the root system, you can think that out of every pair of vectors in the root system, you choose one. Okay, and this is the way you orient the edge between the two players in a tournament. Okay, so here I have an A2 root system, which actually, it lives in 3 dimensions, but it's projected on R2. It's, okay, it's about, like, it's in R3, it corresponds to 3 players. So if I choose E1 minus E2, this is the orientation I choose from the 2, this will correspond to a game between 1 and 2, which was won by 1. Okay, so I can think about orientation of every root system as a tournament. Okay. Yeah, and the idea is that now I take different root systems and consider their orientations in this way. And what you get are exactly the tournaments of types D, B, and C. Yeah, because in D I get 2 pluses or 2 minuses, so this corresponds to both winning or both losing. In B you get also this plus minus EIs, these are like these solitary games. And in C you get 2 EI, which correspond to the loop games. Okay, so it's not as arbitrary as it looked in the beginning. Okay, there is some reason why. Okay, but it will make even more sense if we manage to prove something about these models. Okay, and it turns out that this geometry of root system actually allows you to makes the theorem be true. Okay, so now we'll tell you a bit more about the results for these types. And okay, in classical, for classical tournaments, we had this classification of win sequences. And the crucial sequence was the transitive win sequence. Okay, it was tournament where, yeah, small index was losing with high indices. Okay, so now let me introduce 3 transitive tournaments for types D, B, and C. And it's much less scary than it looks like. Like on top of A-type transitive tournament, I'll just put every collaborative game as a winning game. Okay, so every collaborative game is win. Okay, and this is transitive tournament of type D. Okay, for B, the same, or solitary games won. For C, the same. Okay, and I get some score sequences for these new types. Okay, and what we managed to prove is that, again, you can, using the score sequences, every sequence S is a score sequence of phi type, if and only if it's weak majorized by the transitive score sequence, and there are some parity conditions. Okay, so this is again class characterization of all win sequence in these types. Okay, so yeah, so this is one of the results that we got. But maybe not as exciting as the next result. And okay, now okay, I will focus on these neutral structures. Like, okay, so in classical tournaments, we had cyclic triangles. Okay, I switch them and it doesn't change the win sequence. What are like these structures in these new types? Okay, so since all the competitive edges are there, I will also have cyclic triangles, right? All the competitive edges are there. Yeah, so still, I can have cyclic triangles that I can switch, and they don't impact the score sequence. Okay, so far so good. Okay, In type D, there is one new extra structure. So if you consider 3 players, okay, on the left-hand side, I have collaborative win, collaborative loss, and a competitive win from right to left. Okay, then if you count the scores at each vertex, it's 0. Okay. So if I switch it, it doesn't impact the score sequence. Okay. Now type B. Okay, in type B, I will recall you. Okay, I have competitive, collaborative, and the solitary games. So, okay, I have cyclic triangle. I have this balanced triangle, but also I have 3 kinds of triples. Look like that. Okay. Every solitary game was worth half a point, and every collaborative or competitive edges was giving +half or -half to a player. Okay, so these 3 are neutral in this sense. Okay, and in CN, I have the D type, but also I have 2 other types. Like now this solitary game, it's worth twice as many points. So the structure looks a little bit different. Okay, so now I gave you some simple structures which are neutral. Okay, so fix some win sequence. Fix some score sequence. Let's look at some tournament of this score sequence and count the neutral structures. Okay, so in type D, it turns out that this formula is again preserved, which is a miracle of some kind. I mean, the model just looks super arbitrary, but then it turns out you have some nice invariant. In type B, it's the case as well. And in type C, it's almost the case. So we need to put weight 2 on these 2 neutral structures. And like each of these results, okay, in classical tournaments, you sort of had a quick one-line proof why it holds. Here, it's a little bit more it's not super complex, but it's more complicated. And like I found it like a miracle that you can have formula of such a kind, which looks exactly the same. So maybe takeaway is that okay, it's surprising that you can have such an invariant. Okay, but since we have this invariant, then okay, I can construct interchange graphs for these new types. So strategy is similar as before. If 2 tournaments differ by 1 flip, then I put an edge in the meta graph. Okay, and okay, so because of the counting result, in types B and D, the graphs are just regular, these meta graphs. But in type C, because I needed to put this weight 2, I need to put a double edge whenever I flip this neutral structure involving a loop. Okay, but if I put a double edge, then again, my new interchange graph is also regular. Okay, and also what we managed to prove is that for every score sequence, this interchange graph is connected. Okay, so if it's connected, then you're happy to run your Markov chain. Yeah, and possibly sample. Okay, and since it's regular, it will converge to stationary distribution being uniform. Okay, and this is an example of interchange graph in type C. So I have these double edges for neutral structures involving loops. Any questions right now? Okay. Okay. So yeah. So again, you're happy to run your Markov chain, and what we managed to prove, our like holy grail, was that it does rapidly mix. So in types B and D, the mixing time is just the same as in the classical tournaments. But there was some surprise in type C, which just the naive repetition of the method didn't work because of a reason that I'll hopefully sketch you in a moment. And we needed to do something new. Okay, and yeah, the method is path coupling, just in the classical tournaments case. Okay, so now short time for proofs. Let's drink a little bit. Okay, so what we are going to do is path coupling, but let me maybe say a couple words what a path coupling is. So to prove rapid mixing, we are fighting for having T polynomial in N so that the distance, the distribution is bounded by a small constant. Okay, so the way to find such a T is by what we call coupling methods. And the idea is that, okay, if you want to get to the uniform distribution, then it's actually enough to prove that the distance between any two starting points and T-step transitions is not far. Okay, like a stationary distribution is just average over all PTYs. So this should be fine. And it's also classical in the theory that the distance between these T-step distributions, it can be upper bounded if you find any couplings of the T-step distributions for starting from X and Y. Okay, so the better coupling you find, the better bound you will have. That's the idea. Okay, so ideally you want to find like such a couplings, okay, that will coalesce and quite quickly. Okay, because then this probability will be small and you'll be happy. Okay, so we are fighting for couplings, good couplings. And this probability, it can be upper bounded by just expectation of the graph distance between positions of xtx and yty. Okay? If you are not in the same place in the graph, then you're at least at distance 1. Okay, so we can bound by expectation. Okay, it's the same slide, but was jumping. And now to find a coupling between xtx and xty, it's actually enough to find one-step coupling. Because if you have one-step coupling, then you can iterate it and get multiplicative bound. Okay, so if we find what we call a contractive coupling, which is if you start from two positions and then expectation you decrease the distance, you get closer, then you are in a good shape to prove the rapid mixing. Okay, so we will be fighting for finding contractive couplings. Okay, and the thing is that if you find any contractive coupling, okay, then you can phrase your mixing time in then you're rapidly mixing in terms of proper parameters. Okay, so this is some kind of sketch why we care about these path couplings. Okay, but the thing is that if you start from any two positions in the graph, then it might be hard to describe the couplings. Okay, and there was idea of Babley and Dyer that actually it's enough to show that there are contractive couplings for neighboring states. So if you can find a contractive coupling for neighboring states, then you can chain them together to get long distance couplings. Okay, so more or less the whole problem of finding contractive coupling. We just care about neighboring states. Okay, and benefits are sort of obvious. We need to find less couplings to prove the result. And since the starting positions are neighboring, then the analysis is sort of simpler because you can point out things and just compare them one by one. Okay, so now I will sketch what Max Schein did in her proof of the classical tournaments, which is sort of the same thing we did, but for us, just the combinatorial analysis of the underlying graphs was much more complicated, and this is why maybe this is of interest. Okay, so let me sketch the result for the proof for classical tournaments, what she did. Okay, so what are the neighboring states in the interchange graphs? Okay, these are tournaments which differ by a switch of one cyclic triangle. Okay, so we want to find couplings. Okay, so that if you start at t, this is the x t1, this is x t0 actually, and if you start at t prime, then you want to find, such a describe the joint distribution so that the distance in expectation will get smaller. Okay, so now they are at distance 1, so you will want to somehow define this joint distribution so that in some cases they will coalescent and they will not get too far apart because you want to gain in expectation. Okay, so the way we model the one-step distribution from T is that we just sample uniformly a cyclic triangle, okay, and then we toss a coin. Either we are lazy or we switch the triangle. Okay, and then we get to a new place in the interchange graph. Okay, so suppose T and T prime differ at ABC. And now we'll care about the right-hand side, okay? Depending on the step in the left-hand side, we will define the step on the right-hand side. Okay. Okay, so we differ on ABC. So let's consider cases respectful for ABC, in respect to ABC. So if the sample triangle is disjoint from ABC, then it must also happen in T prime. Yeah, so you switch the same triangle in both, on both sides, and you are still at distance 1, okay, because you still differ at ABC. Okay, this is good. Okay, and now if you sample ABC, this is actually very fortunate for us, because then from T you just go to T prime. Okay, so what you will do, if you sample ABC in T, then you will be, and the coin will decide that you make a move, then you will be lazy in T prime, and vice versa. Okay, so in this case, they will always coalescent. Okay, but there is a third case, yeah? It might happen that the sample triangle intersects ABC, yeah, but it's not ABC. And the problem is that this triangle does not happen in T prime, yeah, because this one edge is switched. Yeah, so we cannot just naively reverse the other one. Okay, so Max Schein was brave and wasn't concerned about this problem. So, okay, so let's look at this triangle, like these cases when you intersect at AC with ABC. Okay, and let's forget about the rest of tournament. Okay, so we just focus on these 4 vertices. Okay, so maybe don't care about what I wrote there. We are flipping the red triangle. Okay, so it gets switched down there. So all the edges are switched. Okay, and now we want to make a move in T prime, so that will not be far from T bar. And the miracle is that actually you can always find such a thing over there. Okay, so in this case, look, okay, you can flip BDC, which is cyclic in T prime. Okay, you get new thing, and then these two new tournaments, they just differ on one cyclic triangle. Okay, so you are still at distance 1. And the miracle is that you can do it for any configuration on these 4 vertices. And there is unique correspondence between cyclic, what you can flip in T and T prime. Okay, so great. So in cases A and C, we stay at the same distance. And in case B, we coalesce them. Okay, so in expectation, we reduce the distance, which is okay. So we have contractive coupling, and we are happy. Okay, yeah, like the first case was B. This is what is my chance of sampling ABC? This is 1 over the number of cyclic triangles that are there. Okay, and there are at most n³ cyclic triangles. Yeah, I have at most n³ triangles. Okay, so the expected distance is smaller than 1 minus cube 1 over n. And the diameter of the interchange graph, so the least number possible of steps to get from one point interchange graph to flip to other tournament with the same win sequence, this is squared in n squared, which was proven by Duraldi and Lee. So by the path coupling, you get the mixing bound, which is amazing. Okay, so this is proof that this algorithm is good. Okay, so what's our story? So it turns out that in types B and D, the structure of interchange graph, it's actually the same as the structure of A in some ways. So, but to prove this uniqueness of correspondence on this tournaments consisting of 4 players, this is messy. But there is such unique correspondence, so you'll finally prove this correspondence. Okay, so yeah. The story is the same. The combinatorics is a bit more involved. But in type C, so in these loops, however arbitrary they are, actually the coupling you can find, we can prove that you are not able to find a contractive one. You can find a coupling that will stay at the same distance, which is not super nice, but okay, it's still enough to get some rapid mixing. But actually, another step in the story. You can get something better. So maybe let me come back a little bit. Okay, so here, when we are in the step of path coupling, okay, here, this distance metric, the fact that it's graph distance is sort of arbitrary, and we don't really care about that it's a graph distance. We care that it's a metric that will give you at least distance 1 between any 2 vertices. So you can adjust this metric to find a better coupling, which is, we are not the first one to do that. It's probably some inspiration of David Wilson, who used this to prove nice result about rapid mixing in Lozenedge tilings. But it's funny that you can do it here as well. Okay. So, okay, and I think it's a good place to stop. So, thank you very much.